We think of space as a vacuum, empty, silent, cold, but if it's a vacuum, how can it have a temperature at all? How can nothing have heat? Well, it turns out that empty isn't exactly the right word. Let's start with what we mean by empty. Space isn't truly empty, not really. Even in the deepest, most remote regions between galaxies, there's a lot going on. You'll find energy, radiation, and a thin soup of tiny particles whizzing around. On Earth, we're used to air molecules bumping into us, transferring heat. In space, there are far fewer particles. It's incredibly thin, almost a perfect vacuum, but it's not truly nothing. Think of it like a giant, nearly empty room. There might only be a few dust motes floating around, but they're still there. This sparse collection of particles and energy gives space its properties, including a temperature. It's just a very low one. So, how cold does it get? In the vast stretches far from any stars or galaxies, the average temperature of space is about minus 455 degrees Fahrenheit, or 2.7 Kelvin. That is incredibly cold, just a couple of degrees above absolute zero. Absolute zero is the theoretical point where all atomic motion stops completely. It's the coldest possible temperature in the universe. But space isn't at absolute zero, it's slightly warmer. This tiny bit of warmth raises a huge question. Where is it coming from? If you're floating in the middle of nowhere, with no stars for light years around, what is keeping the universe from being perfectly cold? The answer is an echo from the very beginning of time. This faint, persistent warmth is the afterglow of creation itself. It's called the cosmic microwave background, or CMB. When the universe was born in the Big Bang nearly 14 billion years ago, it was an unimaginably hot, dense fireball. As the universe expanded, it cooled down, but the light from that initial explosion is still traveling through space today. This ancient light has been stretched out by the expansion of the universe, shifting from visible light into the microwave part of the spectrum. It fills every single corner of the cosmos, bathing everything in a faint, uniform glow. It's a fossil, a relic of a hotter, younger universe. So, no matter where you go in space, you're always being gently warmed by the leftover heat of the Big Bang. The story of the universe is a story of cooling. It started as an infinitely hot singularity and has been expanding and cooling ever since. As space stretched, the energy within it spread out, becoming more and more diffuse. Temperatures plummeted from billions of degrees to the near absolute zero we measure today. But it never reached zero, and it never will. Why is absolute zero impossible to reach? The answer lies in the weird world of quantum physics. According to the uncertainty principle, you can't perfectly know both the position and the momentum of a particle at the same time. If a particle were at absolute zero, its motion would be zero, meaning you'd know its momentum perfectly. This would violate the fundamental laws of quantum mechanics. Even in a perfect vacuum, there are virtual particles that pop in and out of existence, creating tiny fluctuations of energy. This constant, subtle jitter at the quantum level means there's always some energy, some motion, some heat. Nothing can ever be completely still or perfectly cold. So, if space is so cold, why don't astronauts freeze instantly the moment they step out of their spacecraft? It's because of how heat travels. Here on Earth, we lose heat mostly through convection and conduction air molecules bumping into our skin and carrying warmth away. In the vacuum of space, there's no air. Heat can only escape through thermal radiation. It's a much slower process. That's why astronauts wear reflective suits. The shiny outer layers reflect the sun's intense heat, preventing them from overheating. In the shade, those same layers reflect their own body heat back at them, keeping them from freezing. So, for an astronaut, space isn't just cold, it's a place of extreme temperatures. In direct sunlight, surfaces can get hotter than boiling water. In shadow, they plummet to hundreds of degrees below zero, and this variation is true for space itself. Temperature isn't uniform everywhere. Near a star like our Sun, Space is incredibly hot due to the immense energy being radiated. The closer you get, the hotter it is, but as you travel further away, into the space between stars, it gets colder. Travel even further, into the vast voids between galaxies, and you reach that baseline temperature of minus 455 degrees Fahrenheit. Temperature in space is all about the concentration of energy. It's not about how empty a place is, but how much radiation, gas, and dust are packed into it. Understanding the temperature of space isn't just a fun fact. It's crucial for everything we do beyond Earth. Engineers need this knowledge to design spacecraft and satellites that can withstand the brutal temperature swings. A probe sent to Mercury needs a very different design than one sent to Pluto. Astrophysicists use this information to understand how stars and planets form. The cold, dense clouds of interstellar gas are the nurseries where new stars are born. The temperature of these clouds determines whether they will collapse under gravity to ignite a new sun. And by studying the cosmic microwave background, we can learn about the universe's past, its composition, and even predict its ultimate fate. The cold of space isn't empty, it's full of clues. So, while we call it a cold, dark vacuum, space is anything but dead. Its temperature is a memory, a faint whisper of the fiery explosion that created everything. It's a reminder that even in the deepest, most profound darkness, the universe is still glowing. Thanks for watching.